Okay, just I will continue with the last class now. Once again, where we have stopped. Last class we were discussing about the four basic feedback topologies. I mentioned that this is important from examination point of view. Okay, in each of these feedback topologies, few derivations and block diagrams are important. To understand the concept, try to understand the block diagram. Okay, we don't have any circuit diagram, only in some exception cases we may have circuit diagram. Other than that, there is only block diagram in this topic. Okay, so we amplifiers that are available that can be grouped into four categories. Okay, one is among them, there is a voltage amplifier, current amplifier, transconductance, transresistance amplifier. This classification is done based on the quantities such as voltage or current which we are going to amplify, and what kind of output we are expecting from these amplifiers, either it is a voltage or current. So, depending upon the input that is applied and output that we are expecting, based on this the amplifiers can be grouped into four categories. Okay. You might have come across these type of amplifiers prior to this topic, but this topic will give you a more clear idea about different type of amplifiers and in what type of applications we can use them. Okay, voltage amplifier, since we have discussed in last class, I will just quickly go through all these things. Voltage amplifier will have a voltage signal as an input and output, and we call this voltage amplifier as a voltage controlled voltage source. Since output is a voltage, we can represent it with a voltage source. We can model with a voltage source, and so input is also a voltage signal here. Using the input signal, we can control the amplified output signal here. So that's why this voltage amplifier can be interpreted as voltage controlled voltage source. The impedances that we expect from this voltage amplifier is the input impedance has to be very high for the voltage amplifier, and the output impedance need to be very low for the voltage amplifier. When I say input impedance, we are measuring this input impedance between these two terminals here, input ports here, and output impedance is measured between these ports here, output ports here. So for voltage amplifier, this has to be very high. That means input impedance has to be very high and output impedance has to be very low. I also told you the importance of having higher input impedance. Higher input impedance expects little current drawn from the source, and the lower output impedance will give maximum output to the load. So that is the the thing which is important in this for this voltage amplifier. Okay, since input is a voltage source, we can model with its with the Thevenin's equivalent. So we have seen here this Thevenin's equivalent will have a Thevenin voltage in series with the Thevenin's resistance. So these are going to be in series with each other, and the output, we are sampling here. Since this output is an amplified voltage signal, we have to sample, okay, in this way. As you can see, we are doing sampling in the shunt basis or parallel basis here, and this output of this amplifier that goes as an input for the feedback network here. Okay, here there is a feedback network. Every time under each topic we are going to show only the sample of the block diagram. At the end we are going to show complete block diagram of voltage amplifier. Now at the input side, as you can see, since it is represented by the Thevenin's equivalent circuit, the feedback signal also comes back to the input, so that this feedback signal Vf will be in series with the input signal. So these two voltages will get added up, and that is going to be the input for the voltage amplifier. Now we are going to label this with different names. Okay, so these names are very important in understanding the type of amplifier. So you can see here. So output, what is happening is a voltage sampling. So we are sampling the output voltage, and that's what it happens at the output, and at the input we are trying to provide in series with the input signal. So, we are mixing the output signal via the feedback at the input here. So, mixing is happening at the input. So, type of mixing is voltage mixing and type of sampling is voltage sampling, and this we are referring to the output, and this first part we are referring to the input here. So, this type of feedback topology can also be called as voltage mixing, voltage sampling kind of feedback topology. Students has to be familiar with this type of alternative names. Instead of asking this an amplifier as a voltage amplifier, we can also label this amplifier as a voltage mixing, voltage sampling amplifier. Okay. Another name which is given for this type of feedback amplifier is series shunt feedback amplifier. The voltage amplifier is also called as series shunt feedback amplifier. The reason for this is because if you look at the sampling, the type of sampling which is done for this voltage amplifier is parallel. Another name for parallel is a shunt here, and the type of mixing happening at the input side is going to be in series voltage mixing. So, that is why it is called as a series. So, series shunt feedback topology is nothing but a topology for the voltage amplifier, okay, because of series connection at the input and shunt connection or parallel connection at the output. So, this is the overall block diagram for the voltage amplifier, and you can see the type of feedback topology, voltage mixing, voltage sampling kind of feedback topology. In bracket, I have also labeled with alternative names like series shunt feedback topology. Reason is, you can see here there is a shunt connection at the output and there is a series connection at the input here. Due to this feedback topology for the voltage amplifier can also be called as series shunt feedback topology. And the input impedance expected for this amplifier is very high, that is already we said about this. Output impedance expectation is very low. So, these are the key indicators for this voltage amplifier. Okay. And rest of the things you can see here, there is a basic voltage amplifier here and there is a feedback network here. We are sampling in the parallel manner and we are providing input to the feedback network, and the signal from the feedback network goes and adds up with the input signal here Vs. So, this is in mixed with the input signal which is in series, and of course, this Rs is and Rs and Vs, this represents Thevenin's equivalent. Okay. So, this is the block diagram description of voltage mixing, voltage sampling or series shunt mixing feedback topology. Okay. So, there is a lot of advantages of this type of topology, because in general the voltage amplifier it stabilizes the voltage gain. The voltage gain that we are obtaining from this type of voltage amplifier is stable. It does not vary with reference to the transistor parameters or even temperature variations. It maintains constant gain as an output. Higher input impedance which you can expect from this amplifier, and lower output impedance also which you can achieve from this amplifier. These are the key indicators for this to show for the performance of the voltage amplifier here. Now, we have here an example of this series shunt feedback amplifier. Earlier you have seen the block diagram version of the series shunt feedback amplifier. Now, we have a practical circuit here which is based on the op amp here. Okay. So, here students, you might have not studied right now the operational amplifier, but still here we have taken as an example to show that this is a non-inverting amplifier. As you can see here, the input signal which is labeled as Vi, that goes to the non-inverting terminal of an operational amplifier. This symbol shows it is an op amp or operational amplifier. Shortly we call this as an op amp. This is an operational amplifier, and so the op amp has got two inputs which are inverting input, which is indicated with negative sign, non-inverting is positive sign. In this circuit, the input signal which goes to the AC signal goes to the non-inverting input here. So, this type of amplifier is a non-inverting amplifier, and we are grounding this inverting terminal through this resistor which is an R1 here. Okay. So, now this circuit, as I told you, it is an example for series shunt feedback topology. So let us see that how this is an example for series shunt feedback topology. And look at in this non-inverting amplifier where the feedback comes from here. So this is the output port of okay, so non-inverting amplifier. Suppose if you represent this circuit op amp circuit in terms of a block diagram like this. Okay, so this is what we have shown. This is an input, and here we have output. And look at here from circuit point of view, this is an output here, and from here this is the input here. Okay, so even though I say ground is the another part of the input, so this ground and this ground and here the ground are all common, though they are at different places here. Okay, they are common here. So now you can see that we are taking the part of the output through this feedback. Now this is the feedback now. Okay, the signal is given here back to the input here through the resistor R2. R2 is important here because this will control the amount of feedback from output to the input here. Since op amp does not draw any current, I am talking with reference to the ideal op amp. There are two versions of an op amp. One is ideal op amp, which has got ideal characteristics, and the other one is the non-ideal or practical op amp. Okay, so ideal op amp with reference to this input impedance is infinity. That means the current drawn by this inverting terminal and non-inverting terminal are going to be 0. That's what the ideality means here. Okay, so input impedance is infinity, so therefore the current drawn by the op amp is going to be 0. So now here uh, the current which is flowing in this loop is nothing but it is it's Vi by R1, that is the current that is flowing. How do we know that it is Vi by R1? You can see that we have applied here an input signal as Vi for the non-inverting terminal here. As per the virtual ground concept, this point also will be Vi. So this is Vi here. As per the virtual ground concept, we will teach this in the while covering op amp the module. For the time being, you try to understand a few things here itself. So this is a input signal, and since according to the virtual ground, this point also will behave like this according to virtual ground concept here. As long as this op amp is ideal, okay, ideal. We are not using here the practical op amp. We are using an ideal op amp here. So ideal op amp expects the input impedance is going to be infinity. Therefore, current drawn by this op amp is 0. And it tries to make these 2 points the voltage same. Whatever we connect here, the other node will also have same voltage. So in our case, it is going to be the Vi, and Vi by, okay, so this is the amount of current. This is actually the current which is flowing here, Vi by R1 here, as you can see here. So this point is Vi, and the current that flows here is Vi by R1. Okay, so this voltage and voltage at this point is going to be 0. Okay. Okay, so this point is going to be 0. So this voltage minus this is nothing but 0 by R1. So this Vi by R1 is the current that is flowing. If I call this current as say IR1, the current that is flowing through the R1, it is Vi by which is equivalent to the Vi by R1 here. Since the current flowing here is Vi by R1, op amp does not draw any current here. So current going to the op amp is 0. So therefore the current which is coming from this has to be equal to the Vi by R1 only. So therefore this current is also Vi by R1 here. I hope you understand here. So here there are totally 3 branches is there. One branch is going to the ground, other branch is, okay, if you talk practically, this is a branch which is going to the output, but current cannot go like this because this is a feedback, right? So current cannot go like this. Current has to come from the other way, from the output back to the input here, and therefore the current here flowing should be equal to this current here because op amp does not draw any current here. So therefore the current what we have shown here, Vi by R1, the same amount of current has to flow here also. So that is equivalent to Vi by R1 here. So current flowing here and current flow going to the ground, both are same. Okay, so now, so we have to calculate what is the output voltage here. So output voltage is nothing but which is the voltage here, which is the input signal Vi, and the drop across this. Okay, so the drop across this is nothing but Vi by R1 times the resistance which is R2 here. So this is an input signal and this is going to be the feedback signal. So both get added at this particular point here. So V naught, okay, so V naught is nothing but it is Vi plus Vi by R1 into R2. If you take Vi as a common factor from these two terms, so Vi 1 plus R2 by R1 is the resulting equation. So we can write this one as V naught as Vi into 1 plus R2 by, this is nothing but a gain equation here. So if you calculate gain as V naught by Vi, if you take this Vi to the denominator, so you get 1 plus R2 by R1 here. Okay, R2 by 1 plus R2 by R1 is nothing but the gain of this inverting, non-inverting amplifier here. Okay, so we'll talk about this op amp later, but here you should understand the type of feedback. Okay, so it's a output is, we sample it, a voltage and provide that as input as a voltage that gets added up with the input signal. As you can see here, these two signals we are adding up here. Okay, so that shows that the type of mixing happening at the input is it's series mixing. So type of feedback is series shunt kind of feedback. So this is the example of series shunt type of feedback topology. Next we will move on to the another amplifier, which is a current amplifier. So current amplifier is just uh, the signals at the input and output of an amplifier keep changing here. So input signal for the current amplifier is going to be the current signal, that is what we have shown here, and output signal is also going to be the current amplifier. Since input signal is a current signal, so uh, the input can be modeled using Norton equivalent. I hope you are familiar with Norton's theorem, which is very popular theorem in the network theory. So Norton equivalent is represented by the current source parallel with the resistance. This is the Norton's equivalent circuit here. So for the current amplifier, since input is a current signal, so therefore we can represent the input current source with its Norton's equivalent here. Norton's equivalent is the Norton current is INO, this is the Norton's current, and this is going to be the Norton resistance, which is in shunt with the current source here. Okay, so this is what we have an equivalent at the input side here. And output quantity, that is of which is of interest for us in current amplifier, is also a current, because in voltage amplifier we have seen that input is a voltage signal and output is also a voltage signal, whereas in current amplifier input is a current signal, output is also going to be a current signal here. And let us see that what kind of sampling network is suitable for this current amplifier. Since input is current and output is also a current, the feedback network now should sample the output current here. Since output is going to be the current, we expect current sampling, and since input is going to be the current, we expect the current mixing here. We will see how to mix, sample the output current and how to mix that with the input current here. And look at here, the way we sample the output current is shown with this diagram here. So the part of the feedback topology is written here. We have a basic current amplifier which has got input current as input signal as a current signal and output signal also as a current signal. And see, since we have to provide sample the output current signal and provide that as a input to the feedback. So you can see here type of the sampling network that we are using. It is shown here. This is going to be a series kind of the sampling. Okay, so you should be aware of what kind of sampling we use and what kind of mixing we employ here. Since when we sample any current, there must be a loop here. We can't sample like voltage we have done in the previous voltage amplifier case. So therefore the type of the sampling which is shown here is the series sampling here. Okay, so the sampling happens in a series fashion and mixing happens in a shunt fashion here. See, that's below shows that how mixing happens here. Since input we are represented with Norton's equivalent circuit, where there is a Norton current which has got parallel resistance of this current source, and now the signal which is coming from the feedback, you can see here that is mixed in a shunt fashion here. So now we can give based on this the type of sampling we are doing and type of mixing we are doing. Based on that, we can give name here. Okay, you can see that similar to the voltage amplifier, the feedback topology suitable for the current amplifier is what kind of mixing happens here. Current mixing happens at the input and there is a current sampling happens at the output. Since this type of amplifier is a current amplifier, you should see the mixing and sampling what it happens at the input and the output. And now based on the type of mixing, whether it is a series or shunt mixing, okay, since it is a current amplifier, sampling happens in a series manner, and mixing happens in a shunt manner. So therefore, the current mixing, current sampling or current amplifier can also be called as shunt series kind of feedback topology, because shunt is referred to the input which is happening in the parallel fashion of the current mixing, and the current sampling happens in the series fashion here. Remember that these words are very important, and so that students should not forget. Current amplifier can also be called as shunt series kind of feedback topology. The type of feedback topology that is suitable for current amplifier is shunt series feedback topology, because of the parallel connection at the input, that is called as a shunt connection, and series connection at the output, so that is a series connection. Okay, so this name technical words you should remember. Previously we have given series shunt kind of feedback topology for voltage amplifier. Okay, you can remember shortly. For voltage amplifier the name is series shunt. For the current amplifier it is just opposite, it is shunt at the input and series at the output here. If you remember these two things, remaining two amplifiers are very easy, let me tell you. Okay, so if you have any confusions in this, definitely it create confusion even in other two amplifiers such as transconductance and transresistance amplifier. Be clear here itself. Okay, so about voltage amplifier and current amplifier, type of sampling happens and type of mixing happens in voltage amplifier. In current amplifier, what kind of sampling it is happening, what kind of mixing it is happening. So based on this, the remaining two amplifiers can be studied very easily. Okay, now let us look into the block diagram, overall block diagram of this current amplifier or feedback topology suitable for the current amplifier. So look at here, this is a current mixing, current sampling, also called as shunt series feedback topology. This is the feedback topology suitable for current amplifier. Okay, so current amplifier with feedback, you can see that this is the feedback topology. Basic things remain same. There is a basic current amplifier which you are seeing here, and there is a feedback network. We have seen in this in the general feedback structure, and there is a input source. You can see input signal, and there is a load here as you can see here, and here mixing will happen, here sampling will happen. So these are the blocks which you should be familiar in this feedback topologies. Okay, now with reference to this the feedback topology which is suitable for current amplifier, so you can see the sampling which is happening, okay, which is in a series fashion here. Okay, so the current that is I naught which is going back to the amplifier, and then you can see that another current is coming from the amplifier and goes to the feedback. And look at here this IF, all these currents are important because we are going to do few derivations in the coming classes. So this directions of current and this the equivalent representations, all these are important. Okay, should pay attention for these things here. Don't ignore anything that I have shown here, although sometimes I miss out explanation. Okay, so that's why everything is important whatever I put up in the material. Okay, so this is a feedback network, as you can see that this is the output and this is the input of the feedback network. And look at the impedance, what we're expecting from the input side. From the input side for a current amplifier, this is the input impedance expectation is low here, and output impedance is going to be high. When we measure impedance for this current amplifier, output impedance has to be high and input impedance has to be low. This is just opposite of voltage amplifier. In voltage amplifier we have seen that input impedance expectation was higher, output impedance expectation was lower, but in current amplifier it is just reverse. Okay, so output impedance for a good or a better amplifier, output impedance has to be very high, and for the input impedance of current amplifier has to be very low. So these are the desirable parameters of an current amplifier here. Once you design current amplifier, okay, so we need to meet these parameters, desirable parameters in the design. Okay, so this is what it is mentioned here. Input impedance is low and higher output impedance we are expecting. These are the parameters, desirable properties of current amplifier. Okay, so once we do that, let me move on to the another amplifier. which is a transconductance amplifier. Now, if you are familiar with voltage amplifier and current amplifier, now the understanding the topology for the transconductance amplifier will not be difficult. Okay, now let us represent transconductance amplifier as a block diagram, and later we can write the feedback topology which is suitable for transconductance amplifier. In a transconductance amplifier, the input signal is a voltage signal. Look at conductance. What do we mean by conductance? Conductance is nothing but we represent it with G. Don't get confused with gain. This is not a gain. Okay, conductance which is nothing but G. Okay, so which is nothing but I by V. Okay, I by V. This is the conductance. It is a just opposite of resistance, right? Resistance is V by I. Conductance is reverse, reciprocal of that. Okay, since it's a transconductance amplifier. Okay, so input signal is going to be the voltage signal. This is the input signal. Output signal is going to be the current signal. Okay, you should know here we need to sample the current and we need to mix with the input voltage here. Understand here? So just to understand from the definition, it will be very easy. So in a transconductance amplifier, the input signal is voltage signal, the output signal is a current signal as per the definition. So amplifier input is voltage signal, amplifier output is going to be the current signal here. This is shown in the block diagram here. You can see that part of the block diagram we have shown. This is going to be a transconductance amplifier. Okay, we expect input signal to be the voltage signal and output signal is going to be the current signal. There are certain circumstances we will come across. In some applications we may have to design these type of amplifiers. What is the circumstance? What is situation? Suppose if input signal source is available to you and we want to have a amplified current here. Okay, input source available is voltage signal and we need to get amplified current signal. In such kind of circumstance, we need to design a transconductance amplifier. Voltage amplifier or current amplifier are not suitable for this. So only amplifier that is suitable when input signal available is voltage and output we expect is current. In such circumstance, we need to design a transconductance amplifier. Okay, now let us see the overall block diagram or for the feedback topology that is suitable for the transconductance amplifier. Just now we have seen that transconductance amplifier, what is its input signal expectation, what is the output amplified signal type of signal we are getting at the output. So in this case it is going to be the expectation is going to be the current signal and input signal applied is going to be the voltage signal. Now let us see the type of feedback topology that is suitable for this, and we need to sample the current here, as we have shown that for this type of transconductance type of amplifier, output is going to be the current signal, therefore we need to do current sampling. So when I say current sampling, we have seen already in the current amplifier, right? So it has to be happen in the this series manner here, as you are seeing here. And look at here, the input signal for the transconductance amplifier is voltage signal, and here we need to do voltage mixing here. So when I say voltage mixing, now refer to the voltage amplifier. In voltage amplifier, we have seen how to do voltage mixing. So that has to be done in the series fashion, as you can see here, series fashion. Okay, so that's why I told here to refer to the voltage amp, similar to the voltage amplifier. Okay, because in the voltage amplifier also at the input we are doing voltage mixing, and here when looking at the output, so since we are sampling the current, just look at the current amplifier. In the current amplifier also we are doing current sampling. So therefore current sampling has to be done in a series fashion here. So this is a series connection at the output, there is a series connection at the input. So what is the name for this amplifier now? It is series feedback topology. Look at now here below. So series feedback topology. The feedback topology is suitable for transconductance amplifier is voltage mixing, current sampling feedback topology, or this is also called as series feedback topology. I hope these technical words are clear to you. Okay, and look at here this overall block diagram of the transconductance amplifier. There is a basic transconductance amplifier whose output is going to be the current signal and input is going to be the voltage signal. Since output is a current signal, we are doing here current sampling. Okay, and input is going to be the current signal. So so here we need to mix with the input voltage signal. So we are going to do the voltage mixing here. Voltage mixing is done in a series fashion. Okay. Any questions are there? Any questions or any doubts are there? I hope you are clear with the transconductance amplifier. So it is just opposite of transconductance is transresistance amplifier. So let us now understand what do we mean by transresistance amplifier. Transresistance amplifier, the input signal is going to be the current signal and the output signal is going to be the voltage signal. You should understand the type of input signal and output signal for this type of amplifier. So amplifier input is a current signal, output is going to be the voltage signal. So this is the block diagram of the trans resistance amplifier. Output is voltage signal, input is current signal. Now when I say output is a voltage signal, we have to do voltage sampling, and you are already aware that voltage sampling has to be done in a parallel manner. Okay, and look at here at the input side, we need to mix the mix here with the, since input is going to be the current signal, we need to do the current mixing here. So current mixing has to be done in a shunt manner, parallel manner once again. So look at here, this is the overall block diagram of the trans resistance feedback topology for trans resistance amplifier. When we design a trans resistance amplifier, the feedback topology which is suitable for this trans resistance amplifier is current mixing, voltage sampling. So we need to sample the voltage at the output, since it is output is a voltage signal for a trans resistance amplifier. Here we have a voltage signal here, and at this point we have a current signal here. We need to sample the voltage. Sampling is done in a shunt manner, so shunt connection at the output. So when I say shunt connection out of the output, you need to refer to the voltage amplifier. Even in voltage amplifier also, we were sampling voltage signal. Okay, now this sampled voltage signal will go to the feedback network, and here feedback network will provide the gain about beta, and the amplified signal which is coming here should be the current signal here, because we need to do current mixing here, since input is going to be the current source here for the trans resistance amplifier. Look at here, there is a current mixing which is happening, and we have seen this in the current amplifier. Current mixing, same current mixing has to be done in a shunt manner or parallel manner here. So we have here a shunt sampling and a shunt which is mixing here. So therefore this feedback topology is also called as current mixing, voltage sampling, or it is called as shunt sampling or shunt feedback topology. Okay, the explanation is given here, students can refer to that. The presence of parallel connection at the input and output makes this feedback topology as shunt feedback topology. And example for that is going to be the practical example. So this is going to be an inverting operational amplifier that becomes an example for this. As you can see, this is the inverting op amp configuration we have shown, and we represented this Thevenin's model to the Norton model what you are seeing here. Okay, because input the current mixing is happening, therefore we are modeled this as a Norton's equivalent here. So there is no derivation required for this, just the practical circuit shown here resembles the type of sampling which is happening here. It's a voltage sampling and it's going to be the current mixing. Same thing happens even here also. The voltage will get sampled here and it get mixed with the current here. Okay, so you can see here there is a current which is now 0 for an ideal op amp here. This is a current which is going incoming to this, and it's here there are 3 branches which you can see from this particular node. Okay, so this is a practical example of inverting amplifier is a practical example for this shunt feedback topology. Okay, any questions about that? If you don't have questions, let me move on to the next derivation part. So far you have seen the block diagram version of different feedback topologies. Now you will see the equivalent circuit of those feedback topologies with the derivation of the gain, input, output impedance. So this is important again from examination point of view. Students should pay attention for the derivation part and even the this writing an equivalent circuit also. Okay. So let's start with this series shunt feedback topology. This is the feedback topology which is suitable for the voltage amplifier. You have seen this already. So now recap this before we write the equivalent circuit here. Okay. So if you have any questions, I can answer here before we move on to this. So here we will start with derivation here. First, let us take voltage amplifier. Our feedback topology is suitable for the voltage amplifier, which is series shunt feedback topology. Now let us see the ideal case here. So look at here now, instead of writing complete basic voltage amplifier, what we have shown here is an equivalent circuit of the amplifier, which is nothing but called as a circuit here, amplifier equivalent circuit. We know that what are the components of amplifier equivalent circuit. Amplifier equivalent circuit comprises input resistance, a voltage source, output resistance. So these are the three elements that represents an equivalent circuit for the amplifier circuit, A circuit. There is a beta circuit also below, which you can see here. Earlier we have shown this as a block diagram, and many of these elements were hidden in the block diagram. Okay, but now the entire the amplifier circuit, this may be C amplifier, it may be the what should I say, the MOSFET amplifier, common source amplifier, but now the amplifier abstract is represented with this Ri, AVI and R0 here. Okay, though we have seen common emitter amplifier, common source amplifier with different elements in that circuit, the outcome of that circuit, amplifier circuit, either common emitter amplifier circuit or common source amplifier circuit, can be shown with its equivalent circuit like this. An amplifier circuit will have an input impedance, output impedance, and there will be a source voltage here, which provides output voltage here. Okay, so this is the equivalent circuit of a basic amplifier here, and this is the equivalent circuit of feedback network, which is also called as a B circuit. In a nutshell, I can divide this entire block into the entire circuit, equivalent circuit for ideal situation, into the two blocks, which is A circuit and beta circuit. And now all interconnections are done as per our okay, the voltage amplifier feedback topology. As you can see in the voltage amplifier feedback topology, I will just show you okay, from where we have arrived at the ideal equivalent circuit. Yeah, this is the one. You can see here now what we have done in our equivalent circuit is this. We have written the equivalent circuit for this, and we written the equivalent circuit for this. Okay, and the rest all we attached as it is. Okay, you can see here there is a voltage sampling, there is a which is voltage which is mixing, which is done in a series. Shunt sampling is happening at the output. So this series shunt feedback topology, now we are writing with an amplifier equivalent circuit here. Okay, so everything is same. You can see here there is a voltage sampling which is happening here, which is happening in the shunt manner, and there is a voltage mixing which is happening in the series manner here. Okay, so this complete amplifier can be represented with a simple equivalent circuit like this. Okay, as you can see here, and look at here, this we have given a notation as S and S dash here. S and S dash. Look at where they are in the equivalent circuit here. So this S and S dash. So this we are putting a block diagram here. This entire thing we are trying to make another block diagram here. Look at here, this big one here, and there is a O and O dash, as you can see here. So now what you can see, this entire thing, if you put as a block box, okay, like this, what you can see at the input is S and S dash, and we have a source voltage as Vs, and that output, what you can see is the output voltage V naught, and at the point O and O dash, you can see the ports here. So same thing which is here, as you can see, O and O dash, and S dash. Now what is inside this block diagram? Now you can see that inside this block diagram, though here we have different elements, since this is a voltage amplifier with feedback, so therefore we can even write amplifiers with feedback area. So now we have an so this is now, this entire block diagram becomes now voltage amplifier with feedback. Okay, I hope it is clear to you. So here you can see this is a voltage amplifier without feedback. The A circuit is nothing but what we have shown here. This within this, I will show with a different color. This portion within this big block diagram, which we have called here as A circuit. So this is nothing but a amplifier, voltage amplifier without feedback. Without feedback. Okay, and this is going to be the feedback amplifier. Okay, this is a feedback network, I should say here, not an amplifier, it is a feedback network. So this block diagram represents feedback network. Okay, feedback network. Okay, now combining the entire thing represents what? It is a voltage amplifier again with feedback now, because the output of basic amplifier is given back to the feedback network, and again it is applied as an input for the basic amplifier. So this entire thing represents a feedback amplifier. Now the feedback amplifier can be represented with an equivalent circuit here as with RIF, which is an input resistance with feedback, and this is the voltage signal. This is the voltage which is amplified with feedback. See, all these elements you can see with subscript as F here. F indicates there is a feedback. There is a feedback. You can see ROF, ROF. And look at here, there is simply R naught. R naught means without feedback. ROF means it is the output resistance with feedback. And also see here, Ri is nothing but input resistance without feedback. Whereas here, RIF is nothing but input resistance with feedback. Now we have to find a relationship between Ri and RIF. Similarly, we have to find relation at the output side, R naught and ROF. And also we know the relationship between A and AF, right? Anybody remembers what is the relationship between A and AF? What is this? We have shown this derivation in the beginning, right? AF is nothing but A divided by 1 plus A into beta for the negative feedback, right? So we already know the relationship between A and AF, but we don't know the relationship between RIF and RI. Similarly, we want to know the relationship between ROF and RO. So we are going to do that derivation here. So in examination, these relations are very important. Final results, at least, they are very important. So keep try to understand this now. I hope you understand how we arrived at this simple equivalent circuit from this overall ideal equivalent circuit of an amplifier, feedback amplifier for the series shunt feedback topology. Okay. Okay, let me move on to the next derivation part here. So whatever I explained now, it is already shown here. The A circuit is nothing but which is a unilateral open loop amplifier, that is called as an A circuit. The beta circuit is nothing but it is a voltage mixing. The beta circuit is nothing but which is the feedback network. Okay, feedback network that will help us in mixing the sampled voltage. Okay, so for voltage mixing, that is going to be useful here. Okay, unilateral in the sense the amplifier which has got only signal in one direction here. That's why it is called unilateral circuit here. And see the components of unilateral open loop amplifier circuits. We have said here Ri, gain of an amplifier as A, output resistance is R naught here. And a few assumptions we are going to do here. The source and load resistance have been included inside the A circuit here. The source resistance and the load resistance, Ri and R naught, has been included inside the A circuit. That is an assumption what we do here. And the beta circuit does not overload the A circuit. That is another important assumption what we are going to do is the beta circuit what we have shown here, this circuit second part, this circuit should not overload this. What do we mean by overloading? The voltages and currents the provided by this should not get affected within this this amplifier circuit here. Okay, the elements here should not vary the the signals within this amplifier circuit here. Okay, otherwise what happens the DC quantities, everything will change, and you may get different sort of output here. Okay, so the biasing conditions should not change, okay, because of this feedback network. Though they are all interconnected here, um, though we may say ideally this beta circuit will not overload this amplifier circuit, but practically that happens too, but it is a small extent it happens. Okay. Okay, so with these assumptions, we have derivation AF. AF is nothing but, again, you need not do derivation for A, since we already done in the beginning for the voltage amplifier. AF is nothing but which is V naught by Vs, which is given by A divided by 1 plus A beta. This is the gain equation. I showed you already the relationship between AF and A. This is the relationship. And now we need to derive the relationship between RIF and RI. Let us see in what way they are related to each other. So RIF is nothing but which is the input resistance, ROF is the output resistance here. Now let us see the deriving relationship between RIF and RI here. So let us define what is RIF. So RIF is nothing but which is the, yes, yeah, any questions? So RIF is nothing but which is Vs by II. This is the definition. Okay, so now we can see how we get this definition. Look at this again. All these derivations are done with reference to this derivation. You can see here. RIF is nothing but looking at this. We are measuring the impedance. So it is Vs divided by II. Okay, so whatever red line I have drawn here, looking at these terminals S dash and S, and the RIF is defined as Vs divided by II. Okay, so you can see that Vs divided by IA. This is the definition as per the from block diagram. Okay, now we can substitute for IA. What is IA? So IA is nothing but input current going to the amplifier. So input current going to the amplifier is nothing but which is VI by RI. Okay, so we can substitute this relation in this equation in place of IA. Okay, so what you get is RI is equal to Vs by Vi divided by RI, and you can now rearrange this. RI we have taken to the numerator, so RIF is equal to RI times Vs by Vi. Now here we need to apply KVL to the input part of the circuit. You get this KVL equation. This KVL equation you can see from this here. In this loop you can apply KVL equation. This is the loop. Minus Vs plus Vi plus Vf. You can see same equation here. Minus Vs plus Vi plus Vf. This can be written alternatively like this. Vs is equal to Vi plus Vf. We can transfer Vs, Vi and Vf to the other side. And now Vf is nothing but beta times V naught. Okay, so substitute for Vf. Okay, so now you can see once we do that, we also know that V naught is nothing but A times Vi. This is the basic amplifier output voltage equation. Substitute here for V naught. So you get Vs as Vi plus beta A Vi. Vi can be taken as common factor. So Vs is equal to Vi into 1 plus A beta. Now you can see here we have Vs by Vi here, right? So here also we have Vs here and Vi is here. So ratio of that gives you 1 plus A beta. So final equation for RIF is, you can see after substituting, you get RIF as Ri into 1 plus A beta. So this is the end result which is important for us. So for the voltage amplifier or series shunt feedback topology, input impedance with feedback is nothing but input impedance without feedback into 1 plus A beta. Okay, so this is the derivation which you should remember. Most of the times for gate examination they will ask you this. They will give you A value, beta value, Ri value and ask you to calculate input impedance with feedback. As I told in the last class itself, students will forget when they go for pre-final, when they take up gate examination, these formulas, and they may not be in a position to calculate this. Okay, any questions about this? So I'll stop at this point, and next class we'll cover the output impedance of this. Again, output impedance also similar lines we can show that. Okay, So we'll talk about that in the next class, or not. Okay. Any questions so far? I hope it is clear to you till this point, till the derivation of RIF in terms of RI. So this shows that this equation shows that input impedance with feedback increases for an amplifier. Now, is it a good or bad? This, for the feedback amplifier, if input impedance is increasing, obviously it is good advantage for us. Okay, it's an advantage for us for an amplifier. Okay. With that, I will stop here. Next class we will continue with okay, so the output impedance derivation.